Good night. So I'll be doing January 2023 for chemistry paper 2. This is how it looks. Let's not forget that we have 6 questions, 2 sections. You have to answer all the questions. Write your answers on the space provided in the booklet. Do not write in the margins. And where appropriate, you must show all working. You're allowed to use silent non-programmable calculators to answer the questions, and you're given extra paper to write more if you need to. Right? Okay, so that's about it. So it's 7 instructions. So let's get started. Okay, so these 2 papers, one is omitted. So they go here. All right. Now, first question says that you're not supposed to spend more than 30 minutes on it. And here we go. It says, students were required to prepare a sample of the normal salt produced when aqueous sodium hydroxide reacts with dilute sulfuric acid. Define the term normal salt and identify one other type of salt that can be formed from the reaction between dilute sulfuric acid and aqueous sodium hydroxide. Okay, so this is for you. You could try it. You could pause the video and try it. We have the answers now. So define the term normal salt. A normal salt is a salt formed by the complete replacement of replaceable hydrogen atoms from an acid molecule by means of a metal or group of elements acting like a metal. And it says identify one other type of salt that can be formed from the reaction between dilute sulfuric acid and aqueous sodium hydroxide. We have the acid salt right there. And as usual, what is done in CSEC is that they give you some sort of experiment and they lay out everything that was done. So we have here, the normal salt was produced by conducting a titration. The students were provided with a dilute solution of 4.9 grams per dm cube of sulfuric acid, 5 grams of sodium hydroxide, and indicator methyl orange. They carried out the procedure outlined in figures A and B. The titration results of part A are presented in the figure below, which is here. So they use a burette, and we have to know how to read the burette. Now it says, review the procedure for part A for the preparation of a normal salt and answer the questions that follow. Part A procedure. It says, place 5 grams of sodium hydroxide solution in the volumetric flask and add distilled water to make 250 centimeters cube of solution. Pipette 25 centimeters cube of the sodium hydroxide solution and transfer the solution to a conical flask. Add 2 drops of methyl orange indicator to the sodium hydroxide solution in the conical flask. Place the sulfuric acid in the burette and titrate the sodium hydroxide solution until the end point is reached. Repeat steps 2 to 4 until consistent results are obtained. So from the time you see titration questions, I guess you're going to have moles in there. Most times you have mole. So things you need to highlight is like the concentration of sulfuric acid, and you need to note that it's given in grams per dm cube, so you're going to have to convert that to moles per dm cube. You're given the amount of sodium hydroxide inside of 250 centimeters cube of water. So all of that will come into play. Okay, so it says here complete table 1 by using the readings shown in figure 1 on page 6. So looking at the figure here, looking at this figure, we have to fill in the spaces here. And then It says in table 1, indicate with asterisk the titration volumes that will be used to calculate the average volume of sulfuric acid. Then it tells us to calculate the average volume of sulfuric acid using the titration. Then it tells us to also complete the procedure for part B to obtain a dry sample of the normal salt. So you have a bunch of things here to do. And so you should get these answers from the pictures. So from the pictures, you would see, from the pictures you would see right here, as you go down, the number would increase because that's the amount of volume of liquid that will be used. So each point in here is 0.1. So here will be 0.5. So you just keep adding. And then this one will be 25.5. So we have 0.5, 25.5. That's the first one, as you can see here. Then the next one is 12.2. And then we have 37.3. So you have to also read under the meniscus. So the meniscus, I always call the meniscus of water a happy line, happy smile, a smiling line. And you always read below the meniscus here as well. And here we have 15.5, and then we have 40.5. So we have some nice readings. We don't have anything to think about. Sometimes they actually put the reading in between and all that, and you have to think. But this is pretty straightforward. Just remember when you're reading a burette, the number, the value increases as you go down. And here we have it. And then it says, remember we had to put an asterisk on the ones that we were going to use. So I picked numbers that were literally just the same. And I scrapped that one because, I mean, it looks perfect all in all. I would have used all, but those two tells us that it should end at 25. And so to find the average, you would just add up the 2 with the asterisk and divide by the number of values they have, which is 2. To get 25, which would be the same number. Then to get a dry sample of the salt, what you would do, you could do evaporation technique, or you could use simple distillation, but I kept it simple. I said pour the reaction mixture into a large petri dish and allow the water to evaporate over the course of a week. After about a week, obtain the dried salt crystals. So that's how you would obtain a dry sample. Okay, so this is the part that would have probably posed as problematic for some, and that's okay. I mean, it's not really okay, but if you add up the marks, if you don't get it, that'll be 5, 6, 7, 8, 9. It's a lot of marks, but let's see if we could get it from here. So it says, write a balanced equation including state symbols for the formation of the normal salt with sulfuric acid and sodium hydroxide. So that's acid and base reaction. So we know we're going to get water from this and we're going to get a salt. So that's the first thing you need to tell yourself. You also need to tell yourself that you have to include your state symbols. Otherwise, you're going to lose an entire mark. You also need to know how to balance the equation. So if you're doing it right now, try it. And remember those 3 things. You have to know, you have to remember that from an acid and a base, you can get salt and water. You also need to include your state symbols, and you need to balance the equation. That's 3 things. Then the doozy comes at 6, where it says, calculate the number of moles of sulfuric acid used to neutralize the sodium hydroxide. And they give you the molar mass of sulfuric acid and sodium hydroxide. So you don't even have to work out anything there. Then it says calculate the mass of the normal salt expected from the reaction. So you're going to have to go from the theoretical equation and do some equating. Then it says the actual mass of salt obtained by the student was 0.09 grams. So suggest one possible reason for the difference in the expected mass of the salt and the mass obtained. Whew, I am breathless. Okay, so to work this out, let me cover up what I have so that, you know, you can focus. So to work this out, here you have this the acid, and the acid would have, it will be aqueous, because it'll be mixed in water. So H2SO4 plus NaO2 will give you sodium sulfate and water. This is the salt that you're getting here, a normal salt. Normal salts don't contain hydrogen, so this is the salt you get, and it balances. So you have to look across, make sure you have you have 4 hydrogens, 2 and 2, that's 4. 2 sodiums here. We have, for this sulfate, 1 sulfate anion, 1 sulfate anion. And if you count the oxygens, you should have 6. So 2 and 4, that makes 6. 4, you have 2 for here, that makes 6, right? So you balance that equation, that's 3 max. And you put your state symbols, good. Then it says calculate the number of moles of sulfuric acid used to neutralize the sodium hydroxide. So we start off with number of moles of sulfuric acid will be equal to the concentration times the volume. So what you want to do is to convert basically, yes, you want to figure out how many grams is in the 25 dm cube. I think I'll work it out like that. Let me see. Take that away. And I said if 1 mole of H2SO4 has in this mass, then X mole will have in this amount of mass, right? And I worked it out to be X has in, I just cross multiply. So to find, basically, to find out how much mass I had to deal with, I wanted to convert the grams per dm cube to moles. And so I would equate and say, well, 1 mole of H2SO4 will give you this amount of mass. So this is 2H, the mass, 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen to give you this. So when I add these up, I get 4, 5, 6. This is 96, 97, 98, 98, right? And we have it here. So I have 98 here. And then if 1 mole has a mass of 98 grams, then how many moles will have a mass of 0.1225 grams? And so this is literally this, 1 over X equal to 98 over 0.1225. And then we just cross multiply to get this number right here. So this will go up here, this will come down, and that will go up there. Okay? So that's how you do that. So it says calculate the mass of the normal salt expected from the equation, from the reaction. So all you would do now is equate the sulfuric acid to the sodium sulfate, which is a 1-to-1 ratio. So if this is 1 mole to 1 mole, then whatever, theoretically, if you have 0.001225 moles of sulfuric acid, you can get the same thing for sodium sulfate. And then all you would have to do is to figure out the mass of the sodium sulfate. And to figure out the mass, again, all we do is say, well, 1 mole of sodium sulfate has a mass of, let's see, 46 plus 64 plus 16. That will give us, let's see, 10, 11, 12, 126. My math is mathing. And so this would say, this is how it is. It will be 1 over 0.001225 equal to 126 over X. And again, we solve for X. So basically, put the same units on the same side. So if 1 mole has a mass of this, then this would be less because this is smaller than 1 mole. Okay, so we just multiply this by 126 and divide by 1. and we get 0.15435 grams. And so this is pretty close to our 0.09, because it says the actual mass of the salt obtained by the student was less. It was 0.09, which is a little bit less than the 0.01. It's like 0.01 less. So suggest one possible reason for the difference in the expected mass of the salt and the mass obtained. And it says, I said the product lost via transferring from one container to the next. So a lot of times you have product loss via transferring, liquid gets stuck to the containers and all that, and impurities and all that, stuff like that you have. But mostly product loss due to transferring solutions from one container to the next would be the cause of this, okay? Okay, so just note I had a little error here where it should say grams since we're dealing with grams per dm cube. So just note that. So these are the values that you should have gotten. Again, remember when you're trying to find out the number of grams or moles, you can multiply concentration by volume. And remember that the units for concentration can be in grams per dm cube or in moles per dm cube. In this case, it was in grams per dm cube. And so we had to find out how many grams was in the 25 ml. And then we had to find out how many moles was that. And then we equate and all that. So, yeah, I know. Okay, so here is the next question. The next question seemed hard, but it really was a breeze in comparison to the one we just did. It says, one of the main active ingredients in chlorine bleach is the oxidizing agent sodium hypochlorite, NaClO. By adding sodium hypochlorite to water, hypochlorous acid, HOCl, is formed according to the equation below. So we have the equation, yay, and they didn't put the states. Anyway, so it says, state one use of bleach in the laundering of clothes. Everybody know what bleach is used for. So write that down. Define each of the following terms. So be very careful because they want you to differentiate between an oxidizing agent and what oxidation actually is. Then it says deduce the oxidation number of chlorine in the formula NaClO. So you could pause, try the question, and then wait for my answer. So bleach is used to whiten clothing or to make a basically colorless form of the dye of the clothing it is washing. So you could put either or. Then it says define each of the following terms. So an oxidizing agent causes an element in its free state or an element in a compound to lose electrons. Well, in oxidation is the loss of electrons. It is the increase in oxidation state of an element in its free state or an element in a compound. So oxidizing agents cause an element in its free state or an element in a compound to lose electrons. So oxidizing agents gain electrons. And with oxidation, now oxidation is the loss. The actual act of oxidation is the loss of electrons. It is the increase in oxidation state. So it becomes more positive. So for instance, an example of this would be maybe Fe2 plus going towards to become Fe3 plus. So from here we see that this is oxidation. Oxidation is a loss of electrons. So here we would say that if it loses an electron, you put that there, right? And then we just add an electron here. So the actual statement would look something like this, right? But this is oxidation. When you see oxidation go from, it increases, it becomes more positive, that means electrons have been lost. Okay, this is just an example. Now it says here, deduce the oxidation number of chlorine in the formula NaClO. So you have to write each component separately and put X for what we're looking for. So we know sodium is in group 1, so we'd have a +1 oxidation state. We're looking for the oxidation state of chlorine, so that becomes X. And we know the oxidation state of oxygen is -2, and that would override the positive sign, so you just put -2 down. You add 1 and you subtract 2, you get -1, so you get X minus 1. So -2 plus 1 gives you X minus 1. And then you would add 1 to both sides, and we get X is equal to +1. So we know the oxidation state of chlorine. So you could write it out here. Therefore, the oxidation state of chlorine in NaClO is +1. Something like that. 3 marks. Then it goes on and says, chlorine gas also reacts with water to form hypochlorous acid, HOCl, as shown in the equation below, and in which the chlorine has become a chloride ion. What is the change in oxidation number of chlorine for the process? Which process occurred when the chlorine gas became a chloride ion? And describe a simple laboratory test for chlorine gas. So this, again, if you know how to do oxidation numbers and everything, this is pretty straightforward. So whenever we have molecules, the oxidation state of a molecule always be 0. The oxidation state for Cl2 is 0 and water is 0. So that makes it pretty easy for us to see that we're going from a 0 oxidation state to -1, as can be seen here. So they ask, what is the change in oxidation number of chlorine for the process? It's 0, from 0 to -1. So there is a decrease, right? There's a decrease. So we didn't oxidize, we actually became reduced. We went into the negative side of the number line. So they asked, what process occurred when the chlorine gas Cl2 became a chlorine ion Cl-? There was a reduction, right? A reduction occurred. If we were to write the reduction here, you have Cl-. We have 2 atoms of Cl, and we know that reduction is the gain of electrons. So whenever it's gain, what we do is write the addition sign here, and you can leave it like that. So reduction always has the addition sign on the left hand side, and we can leave it just like this. And then of course we'll put in our states. Okay, so there's a reduction, definitely. So when you're going from like 0 into the negative sign, you become reduced, you know. So just note that. So describe a simple laboratory test for chlorine gas. It causes moist blue litmus paper to turn red. So basically bleach your paper, and then it bleaches it white. Yes, so that's the answer right there. A more natural alternative to chlorine bleach is the use of detergents, which release hydrogen peroxide in water. The bleaching action of hydrogen peroxide is also a redox reaction and is represented by the following equation, where we have it breaking down to water and oxygen. That is why hydrogen peroxide is in, well, the reason why it's in brown bottles because of photochemical, what you call it, reaction. Light causes it to break down very easily. That's why hydrogen peroxide is in brown bottles. And so it will break down to water and oxygen. Pretty non-toxic, but this solution is acidic. It turns universal indicator pink. Anyway, during one stage of the reaction, the hydrogen peroxide is converted to water, and it says show the changes in the oxidation number for oxygen in H2O2 and H2O liquid, and deduce whether this is an oxidation or reduction reaction. So again, you're gonna have to write it out. So remember, whenever you have molecules that all have oxidation states of 0, all of these have 0, so you don't have to worry about knowing what the oxidation state of the molecule is in this case. It's not like a sulfate anion where we see that the overall oxidation state for this is -2. Okay, so again, molecules like N2, O2, anything that's a molecule will have overall oxidation state of 0. But the oxidation states of the actual atoms that make up the molecule will be different. So bear in mind of that. So here we do put hydrogen peroxide, hydrogen peroxide. We're looking at this. We wanted to know what was the oxidation state of the hydrogen in hydrogen peroxide as opposed to water. So because we have 2 atoms of hydrogen, we put 2x because this is the unknown. So x we call hydrogen x. And we know that oxygen is in group 6, so we have an oxidation state of -2, and there are 2 atoms of it, so we put the 2 here. And it's all equal to 0, which is the overall oxidation state, like I stated earlier. Then I would say 2x minus 4 because 2 times -2. So this is not 2x because it almost... So this is 2 atoms of oxygen times the oxidation state of oxygen will give us -4, and this negative sign would trump the positive sign, so we just put it in equal to 0. So we're going to remove this using PEMDAS. We go backwards. So we know we have a multiplication operation here and a subtraction operation. So because we use PEMDAS, we go backwards to solve this. So we're going to start with a subtraction, and we do the opposite. So we're going to add 4 to both sides. So now we have 2x equal to 4, and we're left back with the multiplication operation. So the opposite of multiplication will be division. So we divide both sides by 2. We get x equal to 2. For the water, we do pretty much the same thing, but this time we have only 1 atom of oxygen, and everything is equal to 0. And what we get is that the oxidation state of hydrogen in water is +1. So +2 in hydrogen peroxide and +1 in water. And so we see that the hydrogen went from a +2 state to a +1. So therefore this was a reduction reaction. So you see that, right? So we went from +2 to +1. So it went less. So once you get less, it's reduction. Okay? All right. So for this particular paper of 2023, there were 3 questions based on organic chemistry. So I urge you to really study your organic chemistry because I've found that recently they've been putting in more than 1 question for organic chemistry. 2, 3 is almost taking over. So here we have question 3 says, cracking is a very important process in the petroleum industry. What is meant by the term cracking? Then we have compound A, C4H8, and compound B, C4H10, are both hydrocarbons that can be obtained from cracking. State the names of compound A and compound B. Then it says, draw the fully displayed structure of compound A. Okay, so this is basically you have to know this. And then you have to be very careful. We see that the carbon chain has 4 carbons, so we know it's going to be but somewhere there. But for this particular question, we need to know the general formula for each of these. Once you have a number on the H, that can be fully divided by the number on the C and without any remainders, it's an alkene. It belongs to the alkene family. And then once you have that, the number on the carbon goes into the number on the hydrogen with remainders of 2, we know it's an alkane family. So it's always like that. So if I go into this, if I divide 10 by 4, I get 2, remainder 2. So once I have remainder 2, I know it's alkane. Once I have no remainder, I know it's alkene. So from there, you're good. And then you need to remember the general formulas for things like these. And for this one will be CnH twice N. Okay? So that's how you work that out. Cracking is a process by which long-chain hydrocarbon molecules are broken down into shorter-chain hydrocarbon molecules by breaking carbon-carbon bonds. And usually you would have an alkane and an alkene as a product. Then for compound A, by now you know it's butene because it's 4 carbons. Compound B is butane. Draw a fully displayed structure of compound A. Compound A will contain a double bond between the, I drew the wrong structure. I must have been tired. So let me draw the right structure here. So it's butene. So butene means you have 4 carbons and a double bond somewhere. So I would draw it here. And so you make sure 1, 2, 3, 4. Each carbon must have 4 bonds. So this carbon has 4 bonds. This carbon has 3. 1, 2, 3. So we have to add 1 bond here. This carbon only has 2. This carbon has 2. So I've had 2 bonds here. And this carbon only has 1. So we have to add 3 bonds here. So this is butene right here. I must have been sleepy, so ignore this. This is the answer right here. Then it says, state the homologous series to which compound B belongs. And then we already answered that, but if you remember, write it down. Describe briefly one test that could be used to distinguish between compound A and compound B. Write the expected observations. So you have to write the tests here, then you write the observations here. They give you room. You get 3 marks for that. Then it says compound B can exist as structural isomers. Define the term structural isomers. So the homologous series to which compound B belongs is alkanes. And a test that could be used to distinguish the 2 of them would be to use bromine water in a room that is not exposed to light. And what you will see is that only A would decolorize bromine while B would not. Now, if you expose the experiment to light for both of them, A and B will decolorize the bromine, right? So sunlight acts as a catalyst for B. That's the only way B would react with the bromine water. So if you want to get results, you put the 2 of them in a dark room, but a dark room where you could still see, so devoid of sunlight, so that you can carry out this experiment. So it will decolorize the bromine, meaning that it will go from brown to colorless. Compound B says, what is a structural isomer? Compounds that have the same molecular formula but atoms are arranged differently. Okay, yes, you'll see. So it says, in the space provided below, draw fully displayed structures of 2 isomers of compound B. So this is where we're going to explore structural isomerism. And I did the first one as 2-methyl propane. So my longest chain has 3 carbons. I can count my longest chain through here or my longest chain through here. So this is my longest chain. I'm going to go the easy route, and I have a group on the middle C on carbon number 2. And so because of that, I've numbered my chain 1 to 3. Whether I number it from right to left or from left to right, this carbon will still be carbon number 2. And so I put the 2 in front, and then this is called a methyl group because it only has 1 carbon. And so I put 2-methyl propane. That's what goes there. Propane, because the longest chain is 3 carbons long. And then the other isomer would be just butane. Just draw it out, straight chain right like this. And we see here we have 10 hydrogens. 3 on the ends here and 4 in the middle. Well, 3 here, that's 6, and 4 in the middle, that's 10 butane. Now we have here that compound A burns in oxygen with a sooty flame. But compound A, of course, will burn with a sooty flame because it is an alkene. Alkenes, however, do not burn with a sooty flame. They burn very cleanly. Then it says, write a balanced chemical equation for the complete combustion of compound A in excess oxygen. So whenever combustion is involved with hydrocarbons or even with alcohols and stuff like that, the only products you're going to ever get is carbon dioxide and water. And from there you just balance the equation, but you must balance the carbons and the hydrogen atoms first and then deal with the oxygen atoms later. Rule of thumb, just a heads up. So you write back the equation here. You write back the butene plus the oxygen, because this is a combustion reaction. And they're all gases, by the way. And what you get is carbon dioxide and water. And all you have to do is balance the carbons and the hydrogens first. And then once you're satisfied, and once you satisfy the equation, you balance the oxygen. Reason for this is because sometimes you get a fraction. And so once you get a fraction, that is where things go south, and then you would have to basically multiply the entire equation by 2, but that's another story for another day. Question 4. Graphite and diamond add 2 allotropes of carbon. Define the term allotrope. And this was on one entire page. Allotropy is the existence of a chemical element in 2 or more forms, which may differ in the arrangement of the atoms in crystalline solids or in the occurrence of molecules that contain different numbers of atoms. So it usually has to deal with how they are bonded, right? So you could have a compound that contain, in this case with carbon and diamond, with diamond and graphite, they both are only made of carbon atoms. But the way in which they are bonded, the kind of mechanism that involves the bonding, is what makes them who they are, sorry. And that is what they ask here. Draw the lattice structures for diamond and graphite. Now, drawing the lattice structure for graphite is much easier than the diamond, because diamond, anything that comes off as almost 3D is always going to pose a problem. And they're not asking for a unit, they're asking for the actual lattice structure. So y'all have to become artists. So this is my attempt at the lattice structure for diamond, but trust me, this is the unit. So, you know, most people could draw this, but then to go further would have posed a little problem. And I stopped there because I know after a while it's just going to get confusing. Graphite is easy because graphite looks like 2D all over. This is 2D as well, but it appears as 3D after a while when you have to go back, forward, back. Because in all honesty, one carbon is coming towards us and one of the carbons going away from us, and this one is just like flat, like on a planar surface, you know. So something like that. Now with the carbon here, it forms hexagonal rings. They form rings. In this case, carbon doesn't form rings. This is from a tetrahedron, and the tetrahedron is it keeps repeating itself throughout, right? Making diamond really strong because the carbons, each carbon bonds 4 times. It has 4 valence electrons, and all of the carbons bond 4 times. So it's really strong, it's really rigid. Whereas here in this structure, the carbons bond in the catenate, they form rings, and it's 6 of them that come together, and then they stick to each other like this. But as you can see, each carbon only has 3 bonds. If you keep adding, you see that each carbon only has 3 bonds, even though it can make 4, which leaves it electron rich. The entire lattice of graphite becomes electron rich. And also, if you realize, they form sheets which glide over, which makes graphite a great lubricant, and which allows us to write with it, because we can just, you know, write smoothly. And then now I babbled a while ago, and the question asks us, like metals, graphite can conduct electricity but diamond cannot. Explain in terms of bonding why graphite conducts electricity but diamond does not. Describe the bonding present in metals. So you needed to know this stuff. So graphite is able to conduct electricity because it contains delocalized electrons, like what I was telling you. Only 3, it has 4 valence electrons, and of the 4, only 3 are involved in bonding, which leaves the electrons just floating around. So this is because it has 4 valence electrons, but only 3 of them are involved in bonding within graphite, leaving 1 electron free. Once a potential difference, as in once electricity, is applied to, once voltage is applied to the graphite, the mobile electrons are able to conduct electricity by moving along the layers. And I didn't put in this disclaimer there, I mean a little addition here. Whenever they ask you to compare 2 things, you need to talk about the other one. So I put it in here. It says, while all of the valence electrons of carbon in diamond are involved in bonding, and that's why it is unable to conduct electricity, because all of its electrons are involved in bonding, unlike graphite. Now, remember that electricity is really the flow of electrons through a conductor. So once, and it's a flow of delocalized electrons. So if there are no delocalized electrons within a substance, it won't be able to conduct electricity if a voltage is applied to it. The voltage is the push that causes the electrons to do what they're supposed to do. Now, describe the bonding present in metals. Now, we all know that in metals, you have this sea of delocalized electrons surrounding the ions, right? The positive ions. And so the atoms in a metal are packed closely together and are regularly arranged in layers. Metal atoms in a lattice tend to lose their outer electrons and become positive ions. The outer electrons are free to move throughout the lattice. They are delocalized. The metallic bond is formed by the attractive forces between the delocalized electrons and the positive ions. So remember, they look something like this. And they're like together for real in holy matrimony. And then we have these electrons just floating around like a sea. That's what you would see in books, these electrons just floating around. Okay? And then they went and asked you to do this insane task. They said to draw the lattice structure of sodium chloride. What? That's crazy. That's again a 3D structure. And it says which type of bonding exists in sodium chloride. So this, just bear in mind that this is a metal and this is a non-metal. And what do you get when a metal and non-metal bond? You're correct, an ionic bond. So they said to draw the lattice structure, but sorry, I drew the unit. But the lattice structure is real tedious, and I remember learning it in school like this. What it would say is draw 3 boxes, you know, and then there was to connect them, and then you have to run one going like that. And then from there, you have to draw a line down the center. And that line is where I will put my chlorine, right? And so a line will go from the front. You see how tedious it is? And then I would add all these small little bonds in here. 1, 2, 3, 4. It always has 6. So, and then you're going to have a line going across here and across here. So that's a small thing here, right? And then here now will be a big one, and here will be a big one, and then here will be small and small again, big, big, small, and then of course we have a line going here and here. So we have big, small, big, and then big again here. We have this small here, small here, and we have a line here. You see, it becomes ridiculous. And then here, then big here to match here. Then we have big, small. At this point, I would stop there. But that's pretty much how it's supposed to look. But I drew my unit. But that's how you do it. And then you could put a little key and say sodium chlorine. But I have them, so let me fill it in just for good measure. So big circle chlorine, small circle sodium. Then it went on to say ethene undergoes a halogenation reaction. So we are question 5 now. Ethene undergoes a halogenation reaction to form 1,2-dibromoethane. Draw the fully displayed structure of ethane. Write the molecular formula for 1,2-dibromoethane. So they're testing your knowledge on fully displayed and molecular formula, as well as do you know what you're doing? And yeah, you probably do. So ethane. Ethane, first of all, ethene, well, anything eth has only two carbons. So you put your 2 carbons and it says ene. So you have a double bond between there and you just complete the bond. So remember, carbon always has 4. So if you have 2 in here, each carbon going to have 2 bonds to the hydrogen because it's ethene. Then to write the molecular formula of 1,2-dibromoethane. Ethene has 2 carbons and it will have 4 hydrogens, and then that double bond will break to form the bromine, to add the bromine atoms. Now here it says draw the fully displayed structure of 1,2-dibromoethane. State whether the halogenation of ethene is an addition or substitution reaction. So I drew it. And if you didn't know how to write the molecular formula, you could have drawn it here and then go back. So I would start with the C, then the H's, then the big bromine. Then it says state whether the halogenation is addition or subtraction. It's going to be addition. So whenever you have a double bond and you have halogenation, it's always going to be addition reaction. If there's no double bond, then it's going to be substitution, because it's like adding stuff. Okay, we're almost there. So it says dibromomethane can be obtained from methane. This reaction takes place in 2 steps. Write balanced chemical equations to show each step in the formation of dibromomethane. Then state whether the halogenation of methane, key, is an addition or substitution reaction. And then it asks another question. Ethene and propene are typical monomers which are used as starting materials for making polymers. In forming polymers, ethene and propene undergo addition polymerization. Define the term polymer, define the term addition polymerization, and then state one use of each of the following polymers. So what is polyvinyl chloride used for? Another word for polyvinyl chloride is PVC, and then Teflon. You know what this is used for. You hear it a lot. Okay, so we start off with our first reaction. First of all, we're dealing with methane and alkane. So we need a catalyst of UV light. That's the sunlight. And reacting it with bromine. So we're going to remove 1H and substitute it with bromine. And we're going to get hydrogen bromide. The next reaction would be using the product with bromine again. We replace the other H with bromine and we get hydrogen bromide as well. And because it's alkanes, we are substituting, so it's a substitution reaction. Polymers are macromolecules made up by linking at least 50 small molecules, and we call those molecules monomers. Then we said define the term addition polymerization. Now, addition polymerization occurs when monomers containing a double bond, a C to C double bond, combine to form the polymer and no other compound is formed. That's what addition is. Anything addition contains alkenes. And it says state one use of each of the following polymers. So polyvinyl chloride is used as plastic pipe fittings, it could be used in gutters, electrical cable installations. So any of those are giving you 1 point. And Teflon is used in non-stick pans. And now we're on question 6. Finalmente. So the most abundant gas in the air by volume is nitrogen. List one physical property and one chemical property of nitrogen. You have this space there. When gases are produced in a school laboratory, there are 3 main methods in which they can be collected. You can do it by upward delivery, downward delivery, and displacement of water. Guys, you all gotta study your delivery methods for gases and all that. That's a lot. Now, list the 2 factors that should be considered when choosing an appropriate method for the collection of gases in a laboratory. If I didn't know anything at this point, I will use this as my guide and just start to make up something that makes sense. So something you got to write with confidence and just, you know, match it back to what's there. Now state which one of the 3 methods is best suited for the collection of ammonia gas in a laboratory. Explain why each of the other 2 methods would not be appropriate. This question, why did it do this? Anyway, so the most abundant gas in the air. Okay, so we read that. So physical properties that nitrogen is colorless, it is odorless, and it is tasteless. So you write any one of those. And the chemical property is that it has a boiling point of negative 195.8 degrees Celsius. Okay, could have done boiling point, freezing point, density, anything like that. Now, when gases are produced, we already read this. So, listed 2 factors that should be considered when choosing an appropriate method for the collection of gases in a laboratory. 1, you have to decide whether the gas is soluble or not in water. And 2, you have to determine how to collect the gas, which depends on the density of the gas and whether it is denser or less dense than air. So those 2 things are very important. Now, explain why each of the other 2 methods would not be appropriate. So ammonia is less dense than air, so it is collected in the gas jar by downward delivery of air. Ammonia is soluble in water, so it is preferred that it is not prepared using an aqueous solution of an alkali, and ammonia is passed over calcium oxide to dry it. Calcium chloride could not be used because ammonia reacts with it. It cannot be dried with concentrated sulfuric acid because the acid reacts with ammonia to make ammonium chloride. And then we had to draw the actual preparation. So y'all need to actually learn this. It says draw a label diagram of the apparatus which could be used for the preparation of dry ammonia in the lab. Oh my God. They made y'all artists in this exam. And so this is what you do. There's only one drawing. So you need your round bottom flask, your tubing, your glass tubing going on here. And then the gas, because it's lighter than air, will be collected in upward delivery. And then the calcium oxide will be used to dry the gas. Make sure I'm saying the correct thing because at this point I am exhausted. Yes, so sorry. So ammonia is less dense than air, so it is collected in the gas jar by downward displacement of air. So your upward delivery, so you're going to push the air down. So whenever you collect it upward, just write down downward displacement of air. I just think in terms of the sensible way, upward delivery. Anyway, so once you draw this, you're good to go. Here we have the final question. Ammonia is mainly used in fertilizers such as ammonium nitrate. Explain how nitrate fertilizers can be harmful to the environment. Hello. We know what time it is. We're talking about eutrophication. So nitrates can cause eutrophication. Nitrates can dissolve in groundwater and can get into lakes and rivers. Eventually, this can cause the excessive growth of algae. We call them algal blooms, and they can cover the surface of the water. And with that being said, it can suffocate everything in the habitat. So plants start to die, even algae start to die because of lack of sunlight, and then aerobic bacteria feed on the plant remains, and the bacteria multiply. And so the aerobic bacteria use up the oxygen in the water, and eventually, because the water becomes stagnant, the aquatic animals begin to die too, because it's not clean anymore. It's just, it doesn't have any oxygen in it. And that's the end of the exam. Now, wishing you all the best in this year's examination. See you soon.